Okay, I think we can start now, can we? Are you all ready? Or one more minute? Okay, anyway, let's start. So this is the course of Mechanics 1. So to begin with, I will give a brief review of Newtonian mechanics. Now, in the introduction to physics course 1, all of you learn about this and learn about Newtonian mechanics. Now, the most important ingredient of Newtonian mechanics are the Newton's laws of motion, right? Newton's laws of motion. First of all, the law number 1: everybody continues in a state of rest or of uniform motion in a straight line, except insofar as it is compelled by forces to change their state. It means if you experience no forces being acted on, you will continue in a state of rest or continue your uniform motion in a straight line. All right. This first law of motion also is also considered to offer a practical definition of force. Right. Now the second law, that is the law you are most familiar with, and because it is the so-called F equal to ma law. All right, the force is equal to m multiplied by a acceleration. All right, of course, the force is a vector, so the vector F is equal to m multiplied by the acceleration vector, all right, or the rate of change of the momentum vector. Right? The third law: to every action, there is an equal and contrary reaction, or the mutual actions of any two bodies are always equal and oppositely directed along the same straight line. So action and reaction equal but in opposite direction, right? Now here is a question for all of you. If I combine the action and reaction together, what will you get? In other words, we simply add these two quantities together algebraically. What will you get? Action plus reaction. What do you get? 0, 0. Okay. Any more answers? Alternative answers? Or any innovative answers? Now, my question is actually a nonsensical one. Okay, it is purely nonsense because we cannot combine our add action and reaction together because they are acting on different bodies. Am I correct? Not the same body. So my question is purely nonsense. Okay, now keep this in mind. Action and reaction act on different bodies. So these three laws form the pillars of Newtonian mechanics. Have you ever thought about this? Can we derive these three laws from some higher principle? Because we know that these three laws seems to be supported by empirical evidence or experimental evidence. But why they are so. Why they are valid. Say, for example, when we all know about the so-called Kepler's laws, right? After collecting all the astronomical data of the planetary motion, Kepler analyzed them and deduced the 3 laws. But if you ask him why it is so, he could not answer you. Later, when Newton introduced the law of universal gravitation, then we know that the 3 Kepler's laws can be derived from this law of universal gravitation. All right. So we will ask here, can we have a higher principle that will allow us to derive these 3 laws? Later, when we go to when we encounter the Lagrangian and Hamiltonian formulation of classical mechanics, then we will try to offer a derivation, okay, based on some higher principle. Now, these 3 laws, here are some remarks about these 3 laws. The first law is the assertion that inertial systems exist. If it doesn't exist, then it has no meaning at all, right? And also it gives, the first law and the second law can be considered to give a definition of force. The third law states that forces always appear in pairs, and there is no such thing as a lone force without a partner. So whenever we have a force acting on a certain body, we will receive a reaction. Okay. Based on the Newton's laws of motion, we can derive some conservation laws. For example, the law of conservation of linear momentum, the law of conservation of angular momentum, and also the law of conservation of energy, right? If suitable potential energy functions have been defined, right? So for example, a gravitational force, and also the spring, the spring mass, the force of the spring mass system, and say electromagnetic force, electric force, magnetic force. All these will, once we have all these potential energy functions are well defined, then we can derive the law of conservation of energy. Okay, there are some basic steps in analyzing physical problems when we study the Newtonian mechanics. First of all, mentally divide the given system into subsystems, each of which can be treated as a point mass. So if we have a several bodies problem, say for example, we have a trolley or inclined plane, and we have a wheel rolling down. So there's several bodies in the problem. And what we need to do first is to divide them into subsystems, all right, and treat them, each of them, as a point mass. And the second step is to draw a force diagram for each mass, right? So we represent each mass by point and then draw a force vector acting on the mass for each force acting on it, all right? So in this way, we will have a systematic way of analyzing the problem. all right, and writing down the equations. Before doing that, of course, we need to select a suitable coordinate system, which must be inertial. It must be fixed to an inertial frame. Why is this so important? Why is this important? Why must we select a suitable inertial coordinate system? Why can't we choose a non-inertial frame? Okay, now if you don't choose the inertial system, then the physics may appear to be different. All right, if you don't incorporating the so-called fictitious force, appropriate fictitious forces, then what your physical interpretations will be different and will depend on your system. All right, but we all know that the physical laws will remain invariant with respect to all inertial frames. With respect to all inertial frames. All right. So inertial frames are very important for analyzing physical systems. Number 4, if two bodies in the same system interact, the forces between them must be equal and opposite by Newton's third law. These reactions should be written explicitly. All right. So say if you have an inclined particle going down an inclined plane, then the particle will have an action on the plane, on the inclined plane, and also the inclined plane has a reaction acting on the particle, all right, or the body. So we have to put these two forces explicitly on your force diagrams, all right, so that you will not so that you can have a correct analysis. Number 5, in many problems, bodies are constrained to move along certain paths. For instance, a block sliding on a tabletop is constrained to move in a plane. Each constraint can be described by a kinematical equation known as a constraint equation. Each constraint equation should be written explicitly. All right, say for example, you have a sliding block on a horizontal surface. A simple constraint equation will be no motion in the vertical direction. Am I right? No net force acting on the particle or the block in the vertical direction. This is one equation. And if a particle is confined to move in a wire inside a tube, a circular tube, then this is also a constraint motion. So you have to specify this. The radius of the circular motion will not be changed. All right. Now, sometimes the constraints are implicit in the statement of the problem. For example, there's no vertical acceleration for the two blocks on tabletop. So this is the so-called implicit statements. Number 6, keep track of which variables are known and which variables are unknown. The force equations and constraint equations should provide enough relations to allow every unknown to be determined. Now, keep this in mind. We all know that if we have 5 unknowns or 5 unknown independent variables, we must need 5 equations to determine them. All right. If we have only 4 equations, then we are in trouble. There must be 1 equation missing. Or on the other hand, among the 5 variables, unknown variables, 1 of them must be dependent upon the others. So 1 of them is not independent. All right. So finally, all that remains is the mathematical task of solving the equations. Obviously, you have to know about solving second-order ordinary differential equations, right, for a simple system. If you have a coupled systems of 2 particles, you have a system of coupled second-order differential equations. If you have n particles, what do you think? You have a system of n coupled ordinary second-order differential equations.
For example, if you ask me what is the position of the planet Mars in the sky tonight, I will give you the coordinates. I will give you this coordinate.
Can you speak louder? I cannot hear you.
You point your telescope to that direction, and you should be able to find this. Okay, that is.
Okay, last remark, provided that there is a small number of subsystems, these steps can be easily implemented. Otherwise, a smarter approach is needed. But actually, this is all these steps are constitute a systematic approach to tackle most of the problems. All right. Okay, illustrative examples. Say, for example, we have a free particle. We write down the second law, F equal to ma, since F is equal to 0. So we can easily see that the velocity must be a constant vector. And the displacement vector or position vector will be a linear function of time, okay, as given in equation 3. Thus, the particle moves in a straight line with constant velocity. Now, if we choose a frame, an inertial frame, in which the particle is at rest, what will happen? What will you observe? The particle will remain stationary all the time, right? And what is the name of that particular frame? Center of mass frame, all right? A frame co-moving with the particle. All right, second example, particle acted upon by a constant force. So this F is a constant vector. So the velocity is equal to a constant vector plus a vector depends on time linearly, right? And then we further integrate once more and get the displacement vector. And it is a quadratic function of time. Now, if the particle is acted upon by a time-dependent force, it will be more complicated. Velocity, it will involve an integral over time, with the force being the F vector being the integrand. How about the displacement vector? It will involve a double integral. All right, it will involve a double integral. However, we know that we can interchanging the order of integration so that the double integral can be reduced to a single integral in time. All right. So this simple example tells you that if you study basic calculus well, when you are doing research, it will help you a lot. All right. Instead of doing a double integral, you only have to do a single integral. All right. Using the computer. A particle is acted upon by position-dependent force. Now, this is more difficult. Say, equation 7. Sorry, okay. What is your question, Mohammed? Any questions about equation 7?
Can you hear me?
Yes, go ahead.
Yeah, I wanted to ask, like, how did that become from dt prime ft prime to what's below? Like, can you explain that part?
You mean how to reduce the two-dimensional integral into single integral? Am I correct?
Yeah.
So you interchange the order of the integration.
Okay.
So instead of here, you just interchange these two.
No, I mean, like, how did it become from integrating this one part, this dt prime ft prime, to integrating separately, integrating dt prime and dt double prime separately? How did it become from 6 to 7?
You have a function of t here, am I right? This is a
Yeah.
function of t.
Yes.
And we have to integrate it once more.
Okay.
Because the v is dr dt.
Okay.
So we integrate once more. That's why we use the dummy variable t prime.
Okay, that's just a variable. Okay.
Right? Okay.
Okay, I thought t prime meant differentiating t1s.
Okay.
Okay.
Now, a particle acted upon by a position-dependent force. Now, let us look at a very simple one. The force is proportional to the position vector, displacement vector, with a minus sign. Now, the force corresponds to the force acting on a spring mass system, the Hooke's law. Okay, and we know that the solution is given by equation 10 and also equation 11. All right. All of you have learned this before, right? If you find that these two solutions, this solution is unfamiliar to you, then ask your TA in the coming exercise class to derive the solution for you. All right, or you go back to your lecture notes in your previous courses. All right. So the integration constants have been chosen to be initial position and initial velocity. Each component of the position and velocity vectors oscillate about the value 0, because this course will generate the so-called simple harmonic motion. Right? Now, what happens if we have a negative k instead? What happens if we have a negative k instead? Yes, fly to infinity, right? Or negative infinity. So it is not a bounded motion anymore. Number 5, a particle acted upon by a velocity-dependent force. As shown in equation 12, we have a constant force F, small f vector, and also a force proportional to the velocity. All right. Now we need to solve the ordinary differential equation first. Okay, dv dt equal to this in equation 13. We introduce a new variable, capital U vector. Then the ordinary differential equation becomes this. All right, this is a simple differential equation, first order differential equation. We differentiate the capital U vector once and get it back, right? Get it back. So the solution must involve an exponential function. No other choice. Am I right? Now, from now on, forget about the way that you learn from high school to solve this kind of problems. Okay. Now, the common technique that you learn from high school is to move this dt to the right hand side and move the u vector to the left hand side, and then integrate both sides. On the left hand side, you will get a log function of u, right? On the right hand side, you get a linear function in t, and then exponentiate both sides. Okay, that is the way you learn from high school. But now you are a university student. You solve it from another perspective. You differentiate this function once, you get it back. Only one choice, exponential function, right? So you fix this, you introduce an exponential function as a trial solution, and then fix this constant k over m here. Okay. Once we obtain, once we find this capital U vector, we can go to the small v vector easily. And then we integrate equation 14 once more. We get the displacement vector, right? So for large values of time, that means kt over m much larger than 1. The velocity is equal to small f vector divided by k. That means finally we reach a terminal velocity. All right, we reach a terminal velocity. Now, when we say large or long period of time, this is the condition to quantify a long period of time. Why is it so? When we say for a long period of time, we say that it should satisfy this condition. Why is it so? What is m over k? What is m over k? Yes, of course, the exponential part will become 0, as you expected. Right. M over k gives you the time scale of the system. All right. The time scale of the system. When we say something small, something large, something short, something long, we must have a scale, a typical scale of the system. It does not make any sense if we say 1 meter long is a 1 meter long is a long distance, or 1 astronomical unit is refers to a long distance, right? You have to put in context. You have to figure out the typical scale, the length scale of your problem. If you are dealing with astronomical problems, light year will be a good scale for Ning. When you're dealing with planetary motion, 1 AU is a good typical scale. When you're dealing with subatomic motion, what will be the suitable Ning scale? Can you tell me? Can you tell me? Can anyone tell me? When you are dealing with subatomic or atomic system or molecular system. Nanometer, okay. Or in the old days, we like to use that unit. A Bohr radius. Have you ever heard about it? Bohr radius. All right. Bohr radius is a very useful unit in the old days, but nowadays we like the SI unit. All right. Here is an exercise. If the constant force is replaced by a time-dependent force, that means the constant force in this problem, 5, is replaced by a time-dependent force. Please find RT and VT. Okay. Now your TA will ask you this question in the coming exercise class. So you are responsible to provide the answer. All right. So here, this F is no longer a constant force. It is a time-dependent force. So what will happen? What will be the solution? Okay. Number 6, a particle is acted upon by a force which depends on both position and velocity. Wow. Does it ring a bell? Does it ring a bell to you? Have you ever seen such a problem before? Yes. Damped harmonic oscillator, right? Damped harmonic oscillator. So again, when you look at this equation motion, you see that you differentiate the vector R once, you get back something proportional to vector R. You differentiate twice, you get back the R vector again. Okay, something proportional to R vector again. So what will be the solution? It must be an exponential function. Am I correct? I missed something. Here we should have something, a constant vector in front of it. Okay. Otherwise, it is not correct. This is a scalar on the right hand side and vector on the left hand side. All right. So I missed out something. It is a constant vector. Or we just look at one-dimensional problem. Okay. Let's confine ourselves to one dimension. So this is xt instead of r vector t. Can you follow me? All right. So pretend that we are we confine ourselves to one-dimensional problem. Okay. So we don't use a vector to represent the displacement. We simply use xt. Right. So by direct substitution, we will obtain two possible lambda, and each one of them is a complex constant. Okay, complex constant. It is the real part. I call it omega. The purely imaginary part, I call it I gamma. Right. Now it is clear that if for K1 much larger than K2 over K2 squared over 4m, omega is real, but otherwise it is purely imaginary, right? Here is the general solution. Now we have a second order differential equations. So we expect to have two independent solutions. One corresponding to lambda plus, the other one corresponding to lambda minus, all right? So the general solution will be linear combination of these two. Here, the A vector and B vector are arbitrary constant vectors, which will be fixed by imposing the initial conditions. And the velocity will be given by this, by equation 22, via direct differentiating the R vector, okay? And then we impose the impose the boundary initial conditions to fix R naught and also V naught, and A vector and B vectors. All right. Now combining all the details, we finally obtain the displacement at any time t, and also the velocity at any time t. All right. And we find that both of these two quantities oscillate with an amplitude which decays exponentially. All right. Now discuss another exercise for you. Discuss the solution for the excessively damped case. That means 4mk1 is less than k2 squared. And the critically damped case, 4mk1 equal to k2 squared. All right. So this is I believe that you have done this exercise before. So it's a good chance for you to refresh your memory. Okay. Now I finished out I finished the brief review of Newtonian mechanics. Do you have any questions so far? No questions? So can we move on? Okay. Okay. Now we get some review on vector calculus. Divergence. How do we define divergence? We consider a small volume, delta V, of arbitrary shape, which encloses the point that we are interested in, and is bounded by a closed surface, delta S. The divergence of A is defined as the limit of the flux of A through the surface, delta S, divided by the magnitude of the volume, delta V, as the surface shrinks down onto the point. Mathematically speaking, here is the definition of divergence. Okay. In equation 1, del dot A vector is equal to this closed surface integral of A dot ds vector divided by delta V, and finally we take the limit, delta V goes to 0. All right, that is the divergence. Curl, very similar. Imagine a small plane closed curve C of area delta S, cross-sectional area, all right, which contains the point. The direction of the small plane is defined by the unit normal vector. So of course there is a arbitrary there's an uncertainty here. One is there are two directions you can define, of course, but usually we will apply the so-called right-hand rule to define the normal, the unit normal vector, right? With respect to this unit normal vector, apply the right-hand screw rule to define a positive sense of transversal of C. The component of the curl of A is defined by equation 2. So we complete a closed contour integral of this A vector dot dl vector. All right, we compute this closed contour integral and then divide it by the surface area. Finally, we take this delta S approach to 0. Then we get the curl. And the direction of the curl is the same as the unit normal vector. All right, I think all of you have studied this. A famous theorem, Gauss theorem. If we have a divergence of A, then we integrate over a volume containing the A. This volume integral is the same as this surface integral. The dot product between the vector A and also the closed surface, all right, as the integrand, and then we integrate over all surface, the whole closed surface. This is the so-called Gauss theorem or divergence theorem, right? If you have later, you'll find this Gauss theorem or divergence theorem very useful when you study electrostatics. Okay, Gauss law. Stokes theorem. Similarly, will relate a surface integral to a line integral. Okay, so we have the curl of A, and then take the dot product between this curl and also the surface vector, and they integrate over the surface. This integral is equivalent to a closed contour integral of the dot product between the vector A and also the nine element vector dl vector. All right. This is the so-called Stokes theorem. When you study E&M, you realize that this theorem is very useful. All right, for one of the basic law of EM. Which one? Which one? That you can think of. Which one? Can anyone tell me? How about you, Adrian?
Me? Okay.
Yes.
Stokes law is the Beowulf law. The what is the name of that law?
Tina, can you help?
About the magnetic field of a wire.
Okay.
You know the name.
Also. Current.
Someone say Faraday's law. Someone say Ampere's law. Ampere's law.
Yeah, Ampere's law. Yeah,
Ampere's
yeah.
law. Okay. All right. Okay. This is a new theorem for you, for all of you, I think. Helmholtz theorem. Now, consider a vector function which is properly regular and bounded at infinity. So properly regular, I use a layman term. The function is smooth, okay? Smooth function, okay? Bounded at infinity, so no divergence, even at infinity. Usually, that function will decay to 0, all right? Helmholtz theorem states that the vector function C vector can be written as the sum of two vector functions, one of 0 divergence and the other of zero curl. Okay, so that means C can always be written as a sum of two vectors, the D vector and F vector. All right, the D vector has the property that del dot D equals 0, and the vector F has the property that del cross F equals 0. Okay, so that is the Helmholtz theorem. According to this theorem, the D and F can be expressed or defined in terms of two other functions. One is a vector function, the other one is scalar function. So the D vector can always be written as del cross chi vector, all right? And F is the gradient of the scalar function phi. Is it true? Let's see. Del dot D. We know that del cross chi vector must be 0. Why? Because when you take the cross product, you have the direction perpendicular to both chi vector and also the vector, the direction of the del operator, right? So when you take a dot product, obviously you get 0. Now, if you take the curl of F, that means you are going to evaluate del cross del. Then, since they're pointing in the same direction, so we get 0. Okay, know that the vector function is not unique. For the gradient of any scalar function can be added to chi vector without affecting the curl. Is it true? Because if we add something like a gradient of a scalar function, when you take del cross del, it gives you 0. So that's why the chi vector is not unique. Okay, so we take the divergence and curl of equation 5 separately, curl and divergence of C. Divergence of C will give you minus del square phi. The curl of C will give you this, equation 10, all right? Now, what is the solution for equation 9? If you have studied Gauss law in EM, in an EM course, you realize that it is given by this, equation 11, all right? Because this corresponds to the something like the charge density, and each charge has a Coulomb interaction, Coulomb potential, and then you integrate the associated volume, then you get the potential, right? Similarly, we can do the same thing for the equation 10, and you get equation 12 as the solution, all right? Now here, we have to make sure that the integral are finite, provided that the divergence and curl of C both go to 0 faster than 1 over R squared, all right? Why is it so? Why not 1 over R? Why not 1 over R? Why 1 over R squared at least? If it decays as 1 over R, you have logarithmic divergence, am I right? So it won't work. So it must be faster than 1 over R squared, all right? Note that we have taken advantage of arbitrariness in del dot chi vector and set delta dot chi equal to 0 in deriving the second integral. Here, since this chi vector is not unique, so we can always pick a suitable chi in such way that del dot chi is equal to 0. If that is so, then equation 10 and equation 9 will be the same. What does it mean? If this term disappears, then we have 3 equations from equation 10. Each one of them has the same form as equation 9. So each equation has has a solution very similar to equation 11, and we add them together to form a vector. Okay, so that's all for the Helmholtz equation. All right. Helmholtz theorem. So any vector function can be divided into two parts. One, divergence free. The other part, curl free. All right. It is not only useful in classical mechanics, it is also useful in classical EM. Okay. Let's see. Any questions? Now, we have to make sure that both the divergence and curl go to 0 faster than 1/r squared. Okay, why is it so? When you go back, if you look at here, the divergence, why not just 1/r? For 1/r, you still have divergence. Right? Yes, to ensure no divergence. Right? Ensure that the integrals are finite. The integrals are finite, to ensure integrals are finite. All right. Okay. Now, let's see. We still have 5 minutes. Let's see. Should I continue to? Let me see what I have here. Linear algebra. Okay. I think I'll stop here now because this is about the linear algebra, quadratic form. Quadratic form is an important topic. I hope that all I require you all. I require all of you to learn this material, quadratic form. Have you studied the mathematical physics course of Professor Cheng? So you know about this quadratic form, am I correct? Okay, so we can go through it very quickly next time. All right. So I'll stop here. Do you have any questions so far? No questions? Okay. Let me count it 3. No question, number 1. No more question, number 2. Yes, I will talk about talk about the we'll review the linear algebra next time. Okay, in the next lecture on Thursday. So don't worry. Any question? Number 1. Any question? Number 2. Okay. I missed that mathematical physics course. To take as an instrument. Yes, I think how about this? The TAs will discuss the quadratic form or review the quadratic form also in the exercise classes during this week. How about this? Because some of you seem to be unfamiliar with this topic. Okay, I will talk about quadratic form on Thursday, and the TA will answer your questions about this topic as well. How about this? Okay, further discussion on this topic. All right, any more questions? Any more questions? No more? Okay, so I will see you on Thursday. All right, bye-bye.
Just a reminder, there is an exercise class today. Yeah.
Yes, there is an exercise class today in late afternoon. All right. See you on Thursday.